well, actually, it's a very nice textbook problem, but actually there are technologies that actually use this kind of mathematics that you have done here, which is of course the quantum wall. Okay, quantum wall. You can actually make structures that behave like a quantum wall in the sense that you could have I guess compound semiconductor structures, so that the potential seen by the electron is actually slightly different from one part of the compound semiconductor material to another part, so that it resembles a quantum wall. And in the future, you will have to learn the concept of effective mass. And so on, and band structures. What we are talking about here is just an electron moving in free space, moving in the quantum wall. That actually does not exist in the real world. What does exist in the real world is that if you have an electron moving in the lattice, crystal lattice, it is as if this electron is moving in vacuum, but with a different mass. Okay, you will see a different potential too, as it goes from one region of the material to another region. So you will see something like this, but it's something that we will get to later on in the course. But the mathematics is very similar to what you see here, particles being trapped in the quantum wall. So this kind of one-dimensional potential does not exist for a free electron in vacuum in the real world as frequently as you want, but it can exist quite frequently for electron moving in a crystal lattice, like as you can see in some of these compound semiconductor and so on. So, but these are nice mathematical problems that are very similar to your ECE 350 that you have learned. That is just a parallel plate waveguide, and you can have other problems that are somewhat related to your ECE 350, like scattering by a dielectric half space. In ECE 350, you have epsilon 0, epsilon 1. If you send in a light, the light bounces off, and then you have scattering by the dielectric medium. In quantum mechanics, you have scattering by a potential barrier. And so what you have here is that you have a potential jump that looks something like this. And if you send in a particle over here, how does the particle behave? This is very much like that problem over there. Okay, and you know that in this problem, if you do it in reverse order, this is epsilon 1, epsilon 0, at a certain angle, larger than the critical angle, you actually get evanescent wave. The particle, the photon actually does not penetrate into the other space. It just remains in this space. The same thing happens here. If you look at, say, if you have V naught is equal to 0, V naught is equal to V equal to 0 here, V equal to some larger value, say, let me see what I use in the notes, equal to some V naught over here. Okay, if you look at Schrodinger equation, so what you have here is that you have 2m d squared dx squared plus v of x psi of x is equal to e of psi of x. If you look at this equation, vx is 0 to the left, so it's just a free particle moving. But to the right, for x larger than 0, okay, then this equation looks something like this. It's equal to E minus V naught, because this value has V equal to V naught to the right side of x. X is larger than 0. So to the left is just without V naught, to the right you have V naught over there. And it's possible that the right hand side can become negative. Okay, what happens if E is less than V naught on the right hand side? then you have an evanescent wave. Because if you were to solve that equation now, so you have h squared, k squared. If you plug in just a free particle solution, the x squared is equal to minus k squared. And then if you look at the solution of h squared k squared over 2m is equal to e minus b naught. If you just balance this side with that side, you get that equation over there. And then this is negative, which means that k squared is less than 0. K is pure imaginary. So when k is pure imaginary, what kind of wave do we call that wave? Is this evanescent wave, right? So what happens then is that the wave would propagate in an oscillatory fashion, just like a plane wave does. And when it reaches there, it has to exponentially decay. So the wave will look something like that. Very much like this case that we have observed over here. And of course, you can raise E. You can make the particle more energetic as it comes in. Then it's possible that the particle is oscillatory over here. Okay? And then it will still be oscillatory over here. Okay, but K will become smaller actually. It will not have as much energy as it penetrates the thing because its K value becomes smaller. It will have less momentum and hence a longer wavelength. It will look something like that. And of course, with this picture, I should also have a reflected wave. I should also have a reflected wave. There would be a penetrating wave with an evanescent nature. In this case, there will be a penetrating wave with an oscillatory nature, but in both cases, there will be a reflected wave, just like this picture over here. This case corresponds to this case corresponds to that case, and there will be a reflected wave. I guess this is a 350 problem, right? I don't need to solve it mathematically. I can just describe it physically, what happens. You want me to go through the math? I guess it's not necessary, right? You learn it in ECE 350. That's what the math were, and then you just can understand the physics from here. Okay? So this is the scattering by a potential barrier problem. And then you, of course, have this other problem, potential wall, which is the precursor to this problem. If you solve this problem with a different potential barrier on both sides, then it becomes a dielectric waveguide problem. It becomes a dielectric waveguide problem, and you can solve this problem and find the eigenmodes of this thing. But these eigenmodes are very difficult to find. You probably learned from your ECE 350 as to how you can find the eigenmodes of a dielectric slab. Do you remember what you had to do, or did you all go through finding the eigenmodes of a dielectric slab in ECE 350? Did you all learn that, or you all did not? No? No? Okay, maybe sometimes they teach that in ECE 350, sometimes they don't. Okay? So maybe we can just go through the process of finding the eigenmode inside a potential wall. So you have, maybe let me see what I use as a notation. You might have B1 here, B2 here, B3 here. Okay? And then you expect the wave to be a bouncing wave inside, just like a dielectric slab waveguide in here. So inside this region, you will write the solution as being equal to A e to the I k to x I can call this the horizontal axis x plus b e to the minus I k2x. So I can write the solution in the middle region as such. But I expect a trap mode. I expect a trap mode means that these waves are bouncing back and forth, and as they leak outside, they become evanescent. They become evanescent. So I write in this region a solution that is e to the I k3x, where k3 becomes pure imaginary. And this becomes e to the minus alpha 3x. If k3 becomes pure imaginary. And then over here, I expect the wave to be penetrating and traveling in that direction. So I write the solution as e to the I k1x. And I expect k1 to become pure imaginary. So the solution becomes alpha 1x, but with a positive sign there. Because this wave is supposed to decay in the negative x direction as it leaves there. So I would assign an unknown here. Maybe I can call this A2, B2. I will call this maybe A3. I will call this B1. So altogether I have B1, A2, B2, A3. I have four unknowns. Four unknowns that I need to solve for. How can I solve for these four unknowns? I match boundary condition. Okay? And I have two boundaries here. What are the boundary conditions that say x is equal to A and x is equal to B? What are the boundary conditions that I should have over there? We talked about that just a little while ago. So if I were to write the solution in region 1, psi 1x is equal to b1 e to the alpha 1x. And then alpha 1 is the k1 should be equal to, I can figure out k from here. Okay, k is very similar to this. K squared is e minus b over 2m h squared. So k is square root of e minus b over 2m h squared. So that is my k. The k in this region where b is not 0 is given by that equation over there. So k1, by the same token, should be equal to E. I don't know what the energy of this is. I don't know what E should be in this equation. Okay, I don't know what E is as yet in this equation. So E is the eigenvalue of the problem. I set it as an unknown at this point. So to the left, I will have V1 over 2m divided by 1 over h bar. What is that?
There it's in the bottom association.
Let me see, did I get it wrong? H squared
Equal to 2m times e minus b naught over.
Oh yeah, you're correct. Okay. So this should be 2m, right? 2m.
Yes.
This should be 2m. Thank you for pointing that out. So this should be 2m. Let me see what exactly it looks. Yeah, 2m is right. 2m. Okay, should be something. So k1 should be that over there. But I expect that E should be less than V1 over here because the particle is not energetic enough to become a propagating wave over there. So this should be equal to I alpha 1. We expect this to be less than that. And then the wave function in region 2 should be A2 e to the I k2x plus B2 e to the minus I k2x. And k2 should be square root of e minus b2 2m divided by h bar. Okay, that is the wave number that it should have. And we expect the particle is energetic enough so that it can move about. It's propagating. So we expect that this is larger than 0, or that this number is larger than 0, so that K2 is not pure imaginary. And then psi 3x should be equal to A3 e to the minus alpha 3x. Okay, and then K3 is just square root of E minus B3 times 2m divided by h bar. And this should become pure imaginary because we expect the wave to be evanescent over there. Okay, so we expect that to be I alpha 3. And then you have wave function 1, wave function 2, wave function 3. You match boundary conditions at that two locations there. What should the boundary conditions be at the two locations? Yes? Continuity of the wave function itself plus its derivative, right? Because we just eyeball this equation. If the wave function is not continuous, then we'll be in trouble. Okay? Plus its derivative. So we match the two boundary conditions here. Then we have 4 equations. We obtain 4 equations for the 4 unknowns. 4 equations for 4 unknowns. And then you should get something like this. Okay? B1, A2, B2, A3 is equal to 0. You should get an equation that looks something like that. And this equation has no solution. So it's an equation that looks something like this now. The matrix A times x equal to 0. How could I get a non-trivial solution x? How could I get a non-trivial solution x? Eigenvector that has 0 eigenvalue. That's one way to say that. Another way to say that is that the determinant of the matrix A has to be 0. Okay. So this implies that the determinant of A has to be equal to 0. But you notice that E is a free parameter over here. E has not been found. So when you set this, the determinant of A is a function of E. Okay, A is a function of E. And you change E until this determinant goes to 0. Is one way to think about this. But then, these equations are never easy to solve. You can never solve them in closed form. You either have to solve them numerically, graphically, or by some graphical numerical method. There's no closed form solution. If you have done dielectric waveguide before, in the ECE 350, the solutions you obtain there are never in closed form. You have to draw graphs to find out where the solutions are. Okay. Similarly, you have to go to the computer to solve that equation and find out what the solutions are. This is one way to solve this problem. And I won't go into the detail of solving this problem, but I just tell you what the final physics is. Say if you have a potential wall that looks something like this. You have to change your E in order to find different solutions. Say, if you find a solution with the lowest value of E, that E would be the smallest, and then the wave number K2 is not very large. So that is not the most energetic solution. So if I were to sketch the solution where E is the smallest, and that mode will not look very energetic because it will not have a lot of kinetic energy. It will be something that looks like that. I found a solution numerically You satisfy boundary condition at both ends and so on. Then I keep looking and looking, either graphically, using the method you have learned elsewhere, or I go to the computer and write a computer program to look for the next solution. The next solution would be more energetic. Okay, this might be E1, this might be E2, and then it will have more oscillations in it. Okay, and then you keep looking and looking, and then you will find another solution. This is the value of E that you found. You'll find that E is to the E3 now, and then you will have a solution that looks something like this. Okay, E2. And this can only be found numerically. Are there any questions regarding this? So now you know that a potential wall can trap a particle. If the potential wall has infinite potential on the wall, then it's like a parallel plate waveguide. If the potential wall has a finite potential outside the wall, then it's like a dielectric waveguide. That one is an asymmetric dielectric waveguide. It's harder to solve. Okay? This is a symmetric dielectric waveguide. It's easier to solve. But we are not going through the detail of the solution technique because you probably have learned that somewhere else. That technique is purely mathematical. But the physics of it is that this kind of potential wall trap particles. This is the most important physics. And trap particles with different energy levels. The higher the energy level, the more energetic the particle is. Okay? So, but this kind of potential walls are very important in modern technology because of the quantum wall technology, because of the compound semiconductor technology that we can make. We can actually make potential walls using MBE techniques and other kinds of fabrication techniques nowadays. Okay, but there is another potential wall that is very, very important. It's called the potential wall that looks something like this. I can actually, since everything is relative, I can draw the potential wall that go through 0. This is a parabolic potential wall. V of x looks something like this. This is a very, very important potential wall. Because if you trap a particle in this potential wall, the particle will move back and forth just like a pendulum does. Okay? And another thing is that this potential wall keeps going up and up. In principle, it keeps going up and up. So the particle can never leave this potential wall. It's always trapped. This is the potential wall of a simple harmonic oscillator. Okay. Simple harmonic oscillator. So classically, it corresponds to a particle been trapped by a spring constant or been bound to a wall by a spring. So if I have, imagine a wall, and then on this I have a frictionless table, and to this wall I attach a spring, and then I have a mass. And this mass can move back and forth due to the spring, but it can never leave the wall. It can never get quite close to the wall also because of the spring. And classically, we can describe this as a spring constant problem. So if you write Newton's law for this thing, mass times acceleration, if I call this to be my z-axis, okay, mass times acceleration must be equal to the force provided by Hooke's law. This is what we call Hooke's law. I think it's H-O-O-K-E. Okay, as you scratch the spring, it always provides a force in the opposite direction. Okay, And this is called a spring constant, proportional to the stretching. And we can take Z to be measured from the equilibrium point. At equilibrium, this mass is at Z equal to 0 and is to move it to the left and the right. You either insert a negative force or positive force, depending on which direction you're moving. And then the acceleration of the particle is in proportional to the second derivative of its position. And we can also write this equation as being equal to that omega naught square Z, okay, where omega naught square is just K over M. See, I can bring this M to the other side and call my omega naught to be square root of K over M. I think Ian derived something very similar to this for a set of coupled oscillators on a string. Okay, but we're not talking about coupled oscillators on a string, we're just talking about just one of them. Okay? And we know what the solution is. The solution is Z to the A plus or minus E to the minus I omega naught T. Or it can be plus or minus. Okay, if we plug that into the above equation, you have the solution that we often see in the electrical engineering. This is, for instance, the solution of a current in an LC resonator. So we see this kind of simple harmonic oscillator all the time in electrical engineering. We also see that in electromagnetic field. You'll later on find that this harmonic oscillator is very important in describing the electric field, electromagnetic field. Because electromagnetic fields are synonymous with photons, this simple harmonic oscillator is also very important for describing what a photon is. But let's think of this simple harmonic oscillator at this point just as a particle coupled to a wall by a spring. It can be maybe you have two molecules plus an electron, or it can be not two molecules coupled to each other by some molecular force, and then they can also oscillate with respect to each other like a simple harmonic oscillator. But this is the simplest description of this potential well. Okay? So if you look at the potential that we should have in classical mechanics, the potential that we should have in classical mechanics is this potential over here. Omega is the, I can put omega naught, okay, doesn't matter. Omega naught is the oscillation frequency of the classical spring. If you attach this mass to the spring, this will be natural oscillation frequency. And then this is the potential well, and this particle we'll see in classical mechanics. So in classical mechanics, the Hamiltonian is a function of the kinetic energy plus the potential energy. And we'll replace the potential energy V with this quantity in quantum mechanics. So if I were to write down the quantum mechanics equivalence of this, I elevate my T into an operator. I can also elevate my V to an operator, but since this is a scalar quantity, it just becomes the equivalence of a diagonal operator. Yes?
There should be the square in the Z.
You're right. Okay, it should be a square. Thank you for pointing that out. It should be a square in the Z. So if otherwise it would not be parabolic. So I should put a Z here. Okay. So if I were to write this down, then the Schrodinger equation looks something like this. Times, okay, I write this on the second line, En psi of Nz. So if I were to elevate this problem to quantum mechanics, this is classical mechanics, it becomes a quantum mechanical problem. If I were to describe a particle moving about, being trapped by this potential well, that is the Schrodinger equation that the particle should satisfy. And that is the wave function that the particle should have. Okay? So we can solve for the wave function, it turns out that this equation, though it looks complicating, has closed form solution. You will learn how to find a closed form solution in a very systematic procedure later on. Okay, and let me just write down the closed form solution for you. Instead of deriving it at this point, you will learn how to derive the closed form solution later on. Okay, let me just intuit the closed form solution. Well, there will be a solution in the ground state that looks something like this. It will look something like this. Okay. It will be trapped. It will be kind of oscillatory on the inside, and then it will be evanescent on the outside. Then you look at the next energy level and look for another solution. And this one would have a different energy. And then it will be like a trap mode also, but it will look something like this. Okay, let me try to replicate what I have in the lecture notes so that I wouldn't draw a different picture from the lecture notes. So it will look something like this. Okay. So it is like this with a sinusoid. And then if you look at the next one, it will look something like this. Okay. Evanescent outside, oscillatory inside, and then evanescent outside. It goes on and on. Okay. And it turns out that inside the potential wall, in the region where it is oscillatory, you can describe the solution with the polynomial. This looks like a polynomial kind of solution. But outside, the wave has to be evanescent. So it has to be described by an exponential function. It's described by a class of special functions called the Hermite-Gaussian function. Okay. And there are a class of polynomials called the Hermite polynomials. But the Hermite polynomials themselves are not enough to describe the physics, because the solution has to be exponentially decaying outside the wall. So you multiply the Hermite polynomials with the Gaussian function, you get the Hermite Gaussian functions. Okay, it forces the solution to be exponential outside, and those are how the solutions look like. So at this point, I wouldn't derive the solution, but I would just write down the solution for you. This solution is given by 1 over 2n factorial m omega naught over pi h bar, and then multiplied by a Hermite Gaussian function, Gaussian function, not Hermite Gaussian. Okay, Gaussian function. And then multiplied by a Hermite polynomial. The Hermite polynomial is given by this. So this is polynomial part. This is the Gaussian part. And later on we can show that this function, so complicated looking that it is, solve this equation. Okay, solve this equation with a parabolic potential one. Yes?
Is the square root outside going all the way, or is it?
Yeah, it should go all the way. Okay. And what is more wonderful about this potential wall is that all the energy levels are of equal spacing. Okay. Is of equal spacing. It turns out that the first one I didn't draw it quite correctly. The first one actually has something like the first energy level is half h bar omega naught. Okay. The second one is spaced from it by also not half h bar omega naught. The third one is also h bar omega naught. And then you look at the other one, the next one up is also h bar omega naught. Okay? They are all equally spaced. Whereas these are not equally spaced. And the one that is trapped in the square potential valve or infinite potential valve are not equally spaced. But all the energy levels of this very special harmonic oscillator is given by this very special formula, that E sub n is equal to n plus half h bar omega naught. Okay. So because of this, we often associate this energy with the energy of a photon. And then we think of this like as if there are n photons in this system. Okay? N photons. And at this point, you might not appreciate this as much because we are not talking about photons yet. We're just talking about a particle attached to a potential valve. We can be describing this particle that we have here. We don't have a photon at this point. Later on, we'll find that this can be used to describe an electromagnetic system. And that energy can be associated with the energy of a photon. Okay, at this point, the connection is not clear. But what you can think